Hello physics students, this is Mrs. Peachy, your WCA physics teacher, and today we are going to be going through the Conservation of Mechanical Energy Laboratory that is on your agenda for Wednesday of this coming week. And this one deals with potential and kinetic energy, but it's also dealing with different types of mechanical energy, gravitational energy, as well as spring energy. Okay, so let's look a little bit at the different apparatus or gizmo that you're going to be using here and kind of go through what type of data you need to take. But also I want to remind you of the rubric that you're actually going to be using for this. So I know each one of these labs has the CA rubric attached to it, but because of the fact that I really don't like that one, and it has very vague details to it, you need to go to my message boards, click on the only thread, which is the link to my website, and that takes you to Mrs. Peachy's website. Okay, you will click then on Physics A and scroll down until you see the lab rubric right here. Okay, and again, when you bring this up, it is a much more detailed rubric that is much more in line with what you need to do. So the first part of it is your hypothetical and introduction. Your hypothesis. Remember, to get full points on that hypothesis, you need to back it with evidence from the text. So, for example, if you are talking about conservation of energy, you may want to look up the law of conservation of energy and cite that as an example when you're looking at total energy, total conservation of energy in this particular experiment. Data is organized in tables and graphed when appropriate. Like I said, most of the time, if you've got graphable data, graph it. Analysis is calculations. If you need to do any sort of calculations to figure out, say, energy, potential energy, or potential spring energy, or spring constants, that kind of stuff, that's all got to be shown, and that's worth 5 points. And you will, in this particular lab portfolio, show calculations. And then finally, the conclusions, which are the questions that are answered from the actual lesson viewer itself. Okay? So going back to our lesson viewer, the first page is talking a little bit about Hooke's law, and it talks about a spring apparatus, and it says, excuse me, got a little cold here. It says, create a hypothesis of what you think the results of the experiment would be. Okay, so you, in this case, it does not require you to make, oh, let me try that again. I don't want to say the wrong thing. Okay, my bad. First page here, it does ask you to design an experiment that might measure elastic potential energy and gravitational potential energy. So you're going to describe an experiment you could conduct at home, what materials you would use, what measurements you would take, what results you would expect, and basically what sources of error could there be in your experiment. And please note and remember always that saying human error is a cop-out. You can't do that. You're going to have to give me more specific information. What type of human error could be experienced? Typically, we're looking at error in equipment, error in measurement, error in procedure, or error in calculations. Okay, so those are the four main areas, but be very specific about what could you measure wrong, what could you calculate wrong, how the equipment might malfunction, and you know, even including maybe some external variables that weren't properly controlled. So those are some things to look at. So that's the first portion. Then, of course, you're going to make your hypothesis here, which you guys, I'm not going to go through this with you because you understand this stuff pretty well. You're not doing the modification. You will be clicking on the masses and springs here to bring up the Phet simulation. And now you'll be given a lovely screen showing 3 springs, a ruler, and at the bottom a bunch of masses. And over to the left you have all of the different things that you can set. Okay, so you're going to be setting this as basically right now we're on the Earth. You're going to set this so there's no friction. Oh, I'm sorry. You just leave that right in the middle for now. And you'll probably change the time so that you can slow it down a little bit so that you can see kind of where it's going. But let's look at what it asks you to do in the lesson itself, lesson viewer. So, first it says prepare a data table. Label columns trial, mass, stretched spring in meters, highest point in meters, and lowest point in meters. The first column number trials 1, 2, and 3. So you're going to do 3 separate trials. Measure the initial location of the spring relative to the ground using the ruler on the left side of the screen. Measure the distance from the dotted line to the ground. Notice that you can click and drag on the ruler to move it around. So when you do this part, just measuring the initial position of the ruler, see that dotted line? You're going to measure, I'm going to move me over. You're going to measure the position of the dotted line to the ground. And you can assume that the rulers or the weights are sitting on the ground. Okay? So this is approximately, well, 50 centimeters is here, right? And that's 55, 56, 57, 58. So this is 60 centimeters. So it's approximately 60 centimeters. Might be closer to 59, 59.5. Okay? But that's the starting distance of the spring when it is at rest. It should be there. Okay? Then our next step says pick up the 50-gram weight by clicking on it. Hang one of the springs, measure the distance from the dotted line to the bottom of the spring. Also record the mass of the weight in kilograms. Repeat using masses of 100 and 250. Okay, so we're going to go back to the activity here. Get me out of there. I am going to, for now, just kind of move this guy over to this side. Okay, so it says pick up the 50-gram weight. Oopsies. And you're going to hang it on the spring. Okay. Let it stop bouncing. And measure the distance from the dotted line to the bottom of the spring, it says. So it's going to be from here to here, which gives us approximately 5 centimeters. All right, so you're going to measure that distance, and then you're going to repeat this, it says, with a 100-gram and 250-gram masses. Okay, so again, let it kind of stop bouncing all over the place. And then you're going to measure this, and it's about at, oh, looks like it's pretty close to 10, isn't it? 10 centimeters. And then for this guy, my guess is going to be 25. Let's just see. Yep, a 25. So remember, these are centimeters, however. So you're going to need to change that measurement from centimeters into meters. So centimeters to meters. So you're going to divide by 100 because there's 100 centimeters in a meter. So in this case, it would be 0.25 meter. Oh, excuse me. let me just look at that 1 second. You're going to measure, change it to meters, but also change the gram measurements to kilograms. Because we want to make, because remember, if we're going to convert to newtons at all, it's going to be kilogram meter per second squared. So convert your measurements to meters and grams to kilograms. And when you divide by the kilograms, you're going to divide by 1,000 instead of 100, because there's 1,000 grams in a kilogram. Okay. All right, so now it says, replace the 50-gram mass again, and with the mass on the spring, raise it up to the dotted line where the spring rests without a mass on it. Release the mass. Watch the spring closely to identify the high and low points of oscillation. Notice you can slow down the oscillation and pause it using the buttons on the side. Record the highest point and lowest point on your data table. So let's go back and just kind of clarify that real quick. So the spring is normally going to rest right there. Okay, so I'm going to go to selecting over here 1/16th time. Maybe a little too slow, but we'll see. And I'm going to bring this up to where the spring normally rests. Okay, and it normally rests at 0. So my high point, again, we're measuring where the spring is, remember? So I'm going to let it go down. And it comes up to, it looks like it's coming up to pretty much, you know, up to 0.5. And then the low point is about 9, right? So that sounds about right, 0.5 and 9. So I'm going to record those values. And remember, that's centimeters, so convert that. So 0.5 divided by 100. So instead of 0.5, it would be 0.005 meters. And then 0.9 divided by 100, so it would actually be 0.009, right? Yes. Okay, so record those two. Do the same thing with the 100 and 250 gram masses. Those are your high and low points of oscillation. Then, let's move on to the next slide. Now you're going to be doing some calculations. You have to calculate the spring constant. Okay? So using the equation for spring constant, you take the force and divide it by the stretched spring. Now remember that you have to convert the force to, or your kilograms, to newtons in order to get the force. So make sure you multiply whatever the mass is in kilograms times 9.81 to get the force in newtons. Then divide that by the stretched spring in meters. Got it? So you're going to do it that way to get your K. Once you got your K, you can then solve for the elastic potential energy using the equation 1/2 kx squared, where x is the value of the highest point in the oscillation, and then the potential energy at the bottom of the oscillation using 1/2 kx squared, where x is the lowest point of the oscillation. So you're trying to figure out potential energy up here and potential energy down here. And remember, this is elastic potential energy, not gravitational potential energy. And finally, oh, where the heck is it, Miss Peachy? Oh, I'm sorry, I didn't go down far enough. Finally, you are also going to come up with the gravitational potential energy at the top and the bottom of its oscillation. Gravitational potential energy is mgh, so mass times 9.81 times the height in meters above the surface. So this time you're not using newtons, we're using the mass in kilograms, and you're using height in meters. And you're going to compare these. And remember that energy is a vector. So, you know, you're up here, you're down here. Don't forget that they're